we have learned about refraction in the last class. Now we are going to see refraction through spherical lenses. Spherical lens means the lenses, you might have seen the spectacles or the magnifying glass which we are using to read. So if you touch the surface, you can see that it will be bulging out in the middle, and some other lenses are there in which the middle portion is very thin. So spherical lenses are the lenses which are part of a sphere, or one of the surface will be a part of a sphere. It is not necessary that both the surfaces should be spherical. It can be like one surface plane, one surface spherical also. So here what we are going to say about both the surfaces either bulging out or like if it is curved inwards. So two types are there for spherical lenses. One is convex, another one is concave. So first I will show you how is a convex lens looks like. So just think that two spheres we are taking. This is one sphere. This is another sphere. So here you can see the surface which is formed here. It is narrow at the ends and broad in the middle part. So this lens which is formed is known as a convex lens. Convex. So in a convex lens, in the middle part it is bulging out or it is thick, and at the end points it is very thin. So here again we have center for these spheres. These centers we call it as center of curvature or the middle portion. Just like what we have done, just see. So here is C2, here it is C1, this portion we call it as F1, here F2. Actually in lenses we will not write C, instead we will write 2F1. This is written as 2F2, double the focal length it is. So this is the case for a convex lens. Now we will see how a concave lens is formed. So for that again two spheres we are going to take. One sphere. Another sphere. So the lens which is formed like this is known as a concave lens. So here you can see that in the case of a concave lens, in the middle part it is thin and at the end points it is thick. So that is a concave lens. Again here you can see there are centers for both the spheres. This is double the focal length to F1. This is F1. This is F2. This is 2F2. Now you know what is 2F. Okay, double the focal length. So here you cannot say, according to sign convention, we cannot say whether focus is positive or negative, because focus you can see on right side and also on left side. So here we will take just like what we have taken for mirrors. For a concave lens, we will take focal length as negative, and for a convex lens we will take focal length as positive. So that is about concave lens. and convex lens. Hi, so here now we are going to define the focus of lenses. So here I am going to take a convex lens, and this is the principal axis. I am going to take some rays which are coming parallel to the principal axis. Normally we will refraction will happen at this surface and also at this surface, because here it is passing from air to glass, here it is passing from glass to air. So both these sides there should be bending. So here we will not show that separately. We will just draw in the middle point, we will just draw a line, and from the middle this portion where it is touching, we will show that bending. Actually it should be in both these surfaces. So after refraction, it will pass through a point on the principal axis, and this point is known as the focus of a convex lens. So again parallel ray, after refraction it will pass through that point. So this is known as the focus, principal focus of a convex lens. So the parallel rays after refraction converge to a point on the principal axis, and that point is known as the principal focus of the convex lens. So convex lens is also known as converging lens. So convex lens is converging lens. Which mirror is a converging mirror? It is a concave mirror which is a converging mirror. Now here we are going to see the concave lens. For a concave lens, middle part it is thin and end part it is thick. This is the principal axis. A ray which is coming parallel. So here also again draw. So it will diverge after refraction. Now if you extend it back, you can see that it comes from a point on the principal axis which is known as the focus of a concave lens. So here it is diverging. The rays are diverging after refraction. So concave lens is also known as diverging lens. Okay. So a converging lens or a convex lens, the rays which are coming parallel to the principal axis, after refraction it will meet at a point on the principal axis which is known as the principal focus of a convex lens, and it is converging. So we are calling that lens as converging lens. Here the concave lens, the rays which are coming parallel, after refraction it diverges and it appears to come from a point on the principal axis which is not real, it is virtual. So this is also known as diverging lens. Now we will see different types of rays which are needed for drawing a ray diagram. So just like what we have learned in the case of mirrors, here also we will draw different types of rays which are needed for that, and minimum number of rays which are needed for drawing the diagram are 2. So where the 2 rays are meeting after refraction, there the image will be formed. So we will draw the ray diagram for different lenses, and we will see the different positions of the image. So first type of ray, the ray which is coming parallel. Ray coming parallel to the principal axis. So the first type of ray we will draw. So this is a lens. This is the principal axis. A ray which is coming parallel. It will pass through the focus. So this is the case of convex lens, a ray which is coming parallel. After refraction, it will pass through focus of a convex lens. Now next we are going to draw the case of concave. So here a ray which is coming parallel, after refraction diverges and it appears to come from the focus. So this is the first type of ray, the ray which is coming parallel. After refraction it will pass through the focus. And here in the case of concave lens, a ray which is coming parallel diverges after refraction and it appears to come from focus. So that is the first type of ray. Now we are going to see the second type of ray, the ray which is coming through focus. Ray coming through focus. So first we will draw convex lens. This is the principal axis. Here it is the focus. So this is the ray which is coming through focus. After refraction it will go parallel. So that is the for a convex lens. Now for a concave lens we will draw. So principal axis. Now here there is a focus. So a ray which is pointing to this focus. So I will just draw a straight line here. So a ray which is pointing to this focus. So here you can see that after refraction it will go parallel. So here you can see it is pointing towards that focus and it will go parallel after refraction. That is the second type of ray. Now one more type of ray is there. So there we have learned the third type of ray as the ray which is passing through the center of curvature. But here a ray passing through optical center. I will say what is optical center first. Optical center. So here we are going to see a convex lens. This is the principal axis. Here I told you to draw through the middle point. This point is known as the optical center. Okay. So a ray which is falling directly to the optical center will pass undeviated. So that is the third type of ray which is needed. Now here also in the case of concave lens, this is the principal axis. This is the optical center. A ray which is pointing to the optical center, it will go undeviated. So these are the three types of rays which are needed for drawing a ray diagram. First type of ray is a ray which is coming parallel to the principal axis. After refraction it will pass through the focus. Second type of ray is a ray which is passing through the focus. After refraction it will go parallel. And third type of ray is the ray which is passing through the optical center. It will go undeviated. Why it is going through it is undeviated? Because whenever a ray is passing along the normal, that ray will not be having any deviation. For example, if you are taking a surface which is having, for example, a surface separation we are drawing. This is air, this is water. If a ray is falling like this ray will go straight without any deviation, because it is falling along the direction of normal. The one which is falling along the direction of normal will not be deviated. That is the case of refraction. So the ray which is passing along the normal, it will go undeviated. Now you got the idea why it is passing through the optical center without any deviation. So these are the three types of rays which are needed for drawing the ray diagram. And we need any two of these rays for drawing the ray diagram. Switch it. Hi, now we are going to see the image formation by convex lens. So we have discussed now what are the types of rays which are needed for drawing the ray diagram. Three types we have already discussed. Now we will see how the images are formed in a case of convex lens first, then we will see in the case of concave lens. So image formation by convex lens we are going to see. So first position we are taking the object at infinity. So you have already seen in the case of concave mirror how the image is formed when the object is kept at infinity. So here we are going to draw a convex lens. So now the principal axis. Next, draw dotted line. This is the optical center. Here F1, here 2F1. So when you are drawing, make sure that this F1 is the midpoint of these 2 points. Okay. Now here there will be F2 and here there will be 2F2. So here we are going to take some rays which are coming from infinity. That means object is kept at infinity means rays will be coming parallel. So I have taken a ray which is coming parallel. You know that these rays will pass through the focus. Now another ray here. The ray will pass through focus. So here where is the image formed? The image is formed. Position of the image is at F2. So in the second focus it will form the image, and nature of the image, it is nature. It is real, inverted, point sized. So that is the case when object is at infinity. So I hope you understood when the object is kept at infinity. Now in the second case of a concave mirror, we kept it beyond C. Here we have not marked any C. Instead we have 2F1. So we are going to keep the object here beyond 2F1 and we are going to see where the image is formed. So the second object beyond 2F1. So here we are going to draw a convex lens. principal axis, optical center. Now F1 to F1, F2 to F2. So here we are going to keep an object beyond to F1. So this is 2F1. Beyond 2F1 we have kept on object. Now first type of ray, the ray a little more height I will include because okay. First type of ray, the ray which is coming parallel. After a refraction, it will pass through the focus. Now we have to draw another type of ray. Either you can take through F1 or you can take through the optical center. If you are taking through optical center, that will be easy because it is a straight line. So here the image is formed. Straight line, try to draw with the scale. So here the image is formed. Now position of the image is between F2 and 2F2. And what is the nature? It is real, inverted image. Now what about the size of the image which is formed? Size of the image, it is diminished. That means small image is formed. So when we are moving the object towards the lens, the image is moving away and away. In the first case, when the object was at infinity, image was formed at F2. Now when we moved it towards 2F1, that is beyond 2F1, the image from F2, it has moved to in between F2 and 2F2. Next position, we are going to keep the object at 2F1. So you can guess what will happen when we are keeping the object at 2F1. What will happen, you can guess. This is the case just like when we are keeping at C. So object at 2F1. Okay, so here we are going to keep an object at 2F1. So first type of ray, a ray which is going parallel, it should pass through the focus. Second type of ray, a ray which is passing through the optical center. So here you can see that the image is formed at 2F2. So the position of the image, it is formed at 2F2. Nature, real, inverted, and same size as that of object. Real, inverted, same size as that of object. So when we are keeping object at 2F1, the image is formed at to F2. Now you can guess the next case. When you are moving this object from 2F1 to here, that means when the object is between 2F1 and F1, this image will go beyond 2F2. So that image will be real, inverted and enlarged also. So that is next case that you draw as your work. It is a task which is given to you. Now the last case we will do, that is when the object is, it is the second last case, when the object is at focus, what will happen? Object at F1. So object we are keeping at F1. So a parallel ray, it will pass through this focus. Second type of ray which is passing through the optical center, it will go like that without any deviation. So here you can see that this will not meet anywhere, or we can say that the image is formed at infinity. When the two rays are parallel, that means we will say that they will meet at infinity. So it is real, inverted and highly enlarged image which is formed in this case. Now we are going to move this object from F1 to here. That means between F1 and O. That is a special case. So in just like in the case of concave mirror which we have done, the last case is a special case. So object between F1 and O. So here we are going to draw. So we are going to keep the object here. So a ray which is coming parallel, it will go through the focus. I'll just now another type of ray which is passing through the optical center. Here you can see that these two rays will not meet anywhere here because these two are diverging. So what you have to do is you have to extend it back. Now this also you extend back. Where the two rays are meeting, there the image is formed. So here you can see that a virtual, erect, magnified image is formed at the same side of the object. Position of the image at the same side of the object. Now nature, it is virtual, erect and enlarged. So this is a special case in which we will get virtual erect image in the case of a convex lens, just like what we have done for concave mirror. So just compare and learn mirror and lens, so it will be easy for you. So these are the different cases for a convex lens. Hi, just now we are going to see the image formation by a concave lens. So for a concave lens, only two diagrams are there. One we have already drawn, the rays which are coming parallel. After refraction, it diverges and it appears to come from focus. That is the first one, when the object is kept at infinity. Now we are going to see when the object is between infinity to the optical center of the concave. Anywhere when you are placing this object. So here you can see I have placed it here. First type of ray which is drawn is a parallel ray. A parallel ray will diverge after refraction and it appears to come from focus. Now next type of ray is the ray which is coming through focus. You can see that it will go undeviated. And where these two rays are meeting, these two rays are meeting at this point. So I have drawn with the help of a green marker. So here you can see it is a virtual erect which is formed, image is formed in the case of concave lens. So the nature here, it is virtual erect, and what about the size? It is diminished. So virtual erect diminished image is formed in the case of a concave lens. So that is the image formation by a concave lens. Now we are going to see the sign conventions. Sign conventions we have already learned for the case of mirror. The same sign convention is applicable here. So here we are keeping always the object towards the left of the lens. So the light ray is in the right direction. So sign conventions. Sign conventions. So when you are placing an object here, if an object is placed, all the measurements are done from the optical center. So from the optical center, whichever the measurements are towards right, it is taken as positive. Whichever measurements are taken towards left is negative. And this is the principal axis, which is the reference line. From the principal axis, whichever measurements are taken up, it is positive. Whichever measurements are taken down, it is negative. So that is a sign convention for lens also. So now we are going to see different diagrams and what is the sign convention. So the first diagram which we have drawn, it is when the object is at infinity. You can see that the parallel rays after refraction, it converges to a point which is the focus. So here object is at infinity, it is towards left. So U is negative. V means the image is formed at focus. From the optical center O, it is towards right. So V is positive. And focus we cannot say from this diagram. We will just take for a convex lens focal length is positive. So this is the case when object is at infinity. Now object beyond 2f2, 2f1. Second case, object beyond 2f1. So object is kept towards left of the lens. So U is negative, but we are getting the V, that is the image towards right. So V is positive, F is positive in that case also. So only in the last case, that is when object is between F1 and O. Do you remember the diagram? We will just place it here. So here is the object placed. We will get a virtual erect image here. So here in this case, this is the U. So from optical center towards left is U. So U is negative. Now we are getting the image on the same side of the object. We are not getting the image there. Here we are getting the image. So V is also negative in that case. And F is of course positive for a convex lens. So that is the sign convention for convex. Now we will see sign convention for a concave lens. For a concave lens, I hope you remember the diagram. We have kept the lens here. We have kept an object here. So it is diverging. It appears to come from focus. Another type of ray which is going here. So here is the image formed. So object is towards left. So U is negative. V is towards left. So V is also negative. And F focal length, we are taking it as negative. Okay, so that is the case for a concave lens. So that is a sign convention. So according to each diagram, you should be able to identify U, V and F. That is sign convention. Now we will see lens formula. So lens formula, you have already learned mirror formula, right? So lens formula is a relation between object distance. Object distance means the distance between object and the optical center. V, that is image distance. Distance between image and the optical center. And the focal length. Focal length is the distance between focus and the optical center. So in the case of mirror, we were measuring everything from the pole. But here instead of pole, we are measuring from the optical center. So U, V and F has a relation, and that relation is given by 1 by F equals 1 by V minus 1 by U. So this is the relation which is known as lens formula. So in the case of mirror, here it was plus, but in the case of lens, it is minus. Now next we are going to see what is magnification. We have already seen what is magnification in the case of a mirror. Magnification is defined as, it is the extent to which we can enlarge an image. So magnification is defined as height of the image by height of the object. And in the case of mirror, it was minus V by U. Here it is V by U. So this is the case for a lens. Magnification is H dash by H is equal to V by U. That is the case of magnification. Now depending upon the sign value, we can say which is positive, negative and all. Now we are going to see power of a lens. Power of a lens. That is the last portion of this chapter. Power of a lens. When you go for a hospital for eye test or something, they will check your power, eye lens power. And then some problem, if it is there, they will suggest some glasses. So glasses can be for concave lens or convex lens. So depending upon its focal length, we will say the power. So power is defined as the reciprocal of focal length. So power is equal to reciprocal of focal length. But focal length should be in meters. We should state the focal length in meters, then only we can find the power. And the SI unit of power is diopter. Diopter is denoted by D. So 1 diopter can be written as 1 by 1 meter, or 1 diopter is equivalent to 1 meter raised to minus 1. So that is the case of power. So depending on the sign of focal length, we can say the power. So here, if the lens which we are using is a convex, focal length will be positive. So power also will be positive. If your doctor suggested a positive one, so here it will be a convex lens which is suggested. If he has suggested a negative power, that means you are using a concave lens, because power will be negative, focal length will be negative for a concave lens. So this is how we are doing the finding out the power of a lens. So now we will try to do the numericals for this chapter. That is a mix-up of lens formula and mirror formula we will do, and also power of a lens and refraction, absolute refractive index, numericals also we have to do from this chapter. So that's all about today.